Right. Okay, so now we're getting ready to dive back into limits. Now, if you remember in the last session, we did actually briefly start to do limits. We finished all the reviewing from pre-calc. So hopefully, remember what we were doing in that class. And even if not, you can go back and review the slides. Um, and of course, the book is also very good too, and you do have a copy of it. So, but in the meantime, we're going to start the very first new topic of this course, which is limits. And although we did start to look at it the other day, let's go back and revisit what we were doing. Well, it turns out, like so many other chapters in calculus, we're going to start out by introducing a lot of theory, and then we'll go on and learn the rules that we can use to actually do our calculations. Okay, so it's pretty normal for this to be the pattern. We'll start with some background, which is probably very theoretical. And then once we understand that part, we can go ahead and use a set of rules that will help us do this much more quickly and directly. All right, so what do we mean by that? Well, first things first, what exactly is a limit? Well, yeah, if you visualize a function of some kind, it doesn't matter what function it is. What's happening here is basically, let's say here is something simple like y equals x squared. Suppose that we need to know, for some reason, the limit of this function as x approaches 1. Now, this is a very simple case because the function is clearly continuous. And so what that means is that the limit, in this case, and it's written like this, the limit is x approaches 1 of this function. Since the function is continuous, or at least it's continuous at this point, then all you have to do is solve for the function at x equals 1. Okay, so in other words, in this case, it's just 1. Okay. So for continuous functions, calculating limits is going to be very straightforward for the most part. It can get tricky though when our variable, whatever it is converging towards either a very large or small number, if possibly the function is converging to infinity, or especially if there are discontinuities in the function, then we can have some tricky calculations ahead of us, let's say. So as far as this goes, the notation here, this is pronounced in English, the limit of x squared as s approaches 1. So there's now, by the way, I do want to point out here that x can approach 1 from two different directions. If x is increasing, x is approaching here 1 from the left, it's called. And that means what you're solving for here, you see this little negative sign, that is there to indicate that we're approaching 1 from the left. This would be, of course, the opposite. In other words, it's starting at the large numbers and working its way down to the to 1. And so the way we write that is the limit as x approaches 1 from the right. Now, we don't normally write it separately like this unless there's a good reason for it. If you notice here, we don't have either plus or minus 1. That indicates that it's the same coming from both directions. Okay, and you can see that visually from this graph. So in other words, we don't need to make a distinction between approaching from the left or the right, because either way, it'll give us a 1. But in some cases, that's not the case. In other words, the two can be different from each other. And so sometimes it's important to be able to indicate which direction we're coming from. And some of our results will depend on, whether we're approaching from the left or from the right. So most of the time we'll see this notation, but sometimes we'll need one of these two. Okay, now here's a good example of this. Now look at this thing. It doesn't look terrifying, but if you notice, we can't allow x to equal 1. Uh-oh, we're in trouble now because we have to recognize that if we're trying to solve for the limit as x approaches 1, we're going to have a problem because we can't have division by 0. So let's go to Symbolab and see what this function looks like. Um, let's see what this is. Y equals x cubed minus 1 over x. And if Symbolab draws a proper, you'll see there's a bit of a problem right there. Okay. So what it's trying to tell us here is this. The domain of this function is all real numbers except x equals 1. We can't allow the domain, or x to equal 1, it can't be in the domain because that would lead to division by 0. So the way they indicate that is with this hollow circle here, which means that the function is defined everywhere except exactly at that one point. So you got a 0 here. I mean, a blank. Well, you think of it as a blank space. And so that is a sign to us that the function is discontinuous. So we have to be careful about how we approach the limit. Now, I do want to point out, though, that if you do long division in this case, let's go back and get some practice with long division. We haven't done that since pre-calc. And try to divide x minus 1 into x cubed minus 1. It's possible that x minus 1 is a factor of x cubed minus 1. How do you find this out? One way you can try out or test this idea is to simply use long division. If there's no remainder, then x minus 1 is in fact a factor of x cubed minus 1. So let's find out if that's the case or not. By the way, when you're doing the long division, you notice how there's no x squared or x terms in the numerator. We need to put in a 0 as a placeholder in order to make this process work. So the first thing I want to do is multiply x minus 1 times something that will let me eliminate this x cubed. And so I'm going to try x squared, put it here. If I multiply x squared times x minus 1, that leaves me with x cubed minus x squared. And now that expression has to be subtracted from the terms directly above it. So you got to watch out because if this becomes negative, these drop out, this becomes positive, and you're left with x squared. You bring down this 0x. Now I'm going to try x times x minus 1 is negative x squared. Subtract, add, and then guess what? The last term is just plus 1. So what does this prove? All right, what it tells us is this. If you divide that out, you'll get x squared plus x plus 1. Okay, so if this was the original function that we started out with, we'd have the same graph except that there wouldn't be a hole there because here the domain is all the real numbers. Okay, so that's what really separates the two cases. Just like not positive I'm sure that correctly. Yeah, it should have been up a little higher. Let me move this up just a little. No, I can't do that. All right, I'll just start it all over again. I just realized it isn't quite correct. Um, let's go back to symbol lab for a second. Yeah, the intercept is right here. All right, and it cuts through the axis at 1. So let me make sure that it does the same thing happens here. Okay. All right, so let's try that one more time. Okay, that's better. So there's a discontinuity here, okay? But over here, there is one. So this circle wouldn't normally be drawn here. I mean, you would just have the curve, but I just want to make it clear that if you're using this is your function, then when you evaluate this when y equals x equals 1 rather, so this is part of the function. In other words, x equals 1 is part of the domain. So here the domain is all real numbers. Here's everything except 1. Remember, we reviewed this a while back, this interval notation it's called, where you have the union of two sets, two infinite sets, negative infinity up to but not including 1, and 1 up to infinity not including 1 again. So the 1 is not part of the domain here. So now, interestingly enough, you might be surprised to discover, though, that in spite of this discontinuity, in this case, the limit as x goes to 1 is actually 3, as it is on the left. So now that is strange. Now, the reason for that is because as you come from the left, it's the same as coming from the right. So the way limits are defined, we'll get to the formal definition in a minute. When we're converging to a certain point, if the function is defined everywhere except possibly at that point itself, we still have a limit. Okay, in other words, as long as everything else is fine except that one point, we still have a limit. So the limits of the two examples are both the same, in spite of the fact that we have a discontinuity on the left and we do not have one on the right. Okay, and if you notice, on the right, all we did is plug one into this formula. We're all set. Over here, we just see by looking at the function that it's getting awfully close to 3. And in the slides, they encourage you to do it by actually calculating values of x coming from both directions. Yeah, here, like in this little table here. Now, you can do this without taking all day. You can just plug it into Excel. So I'm just going to do this real fast for you. X cubed minus 1. I'll fix that, clean that up in a second. There's a way to make these create superscripts in here. So it looks right. All right. Oh, and I also forgot the parentheses. So because this is our function, what I'm going to do is use their values, where they have 1.75, 1.9. So clearly what you're seeing here is approaching from the left. And what they want you to do, oh, I'm sorry, this is a different example. I just noticed that. All right, but we can still do it here. I'll tell you, I just realized it's not the same example. Let's do this. Now we know that it's one, the function will be undefined. So we'll jump ahead to 1.001, 1.01, 1, 2. So in other words, it should be clear by looking at the results happening to it. So in other words, here, if you notice, as I'm coming from the left, um, the function is getting awfully, awfully close to 3. As I'm coming from the right in this direction, it shrinks down to almost 3. Okay. And in fact, I can get as close as I want to. I can have 1.0000001, that kind of thing. And you'll see that they're both getting really, really close to 3. And so in the limit, no matter which direction we're coming from, the limit of this function is 3. Okay, that's what it's converging to. So we define the limit as simply 3. Now for this one, they wanted us to fill in the same kind of table and just say, well, what do you know? I guess we could try that one. What is this? X squared minus 3x plus 2, and all of that is divided by x minus 2. So clearly, whatever this function is, it will not be defined. It will have a discontinuity when x equals 2. But that doesn't mean that it doesn't have a limit. Now, before I fill in this table, let's take a look at Symbolab, and we'll be able to tell right away what it's supposed to be. Oops, up here. So once again, it was x squared minus 3x plus 2 all over x minus 2. Very good. So as you can see, this reduces to a linear equation. If you were to divide x minus 2 into the numerator, you'll see what happens. I'll do that with you in a second, but you can see when we reach 2, there is a discontinuity because of the fact that that would lead to division by 0. Now, while we're at it, why don't we do some long division and see what happens when we divide. Oh, I grabbed this. We're going to need this in a few minutes, that terrifying looking graph down there. I put it there because we'll need it in a bit. But we'll get back to that in a bit. We'll save it for later. X squared over x minus. So try some long division. Start with x. And remember, we're subtracting. This becomes negative, this becomes positive. So we have negative x plus 2, so minus 1. That'll do the job. So what that means is this ratio reduces to x minus 1, which is obviously a linear function. So if that was our original function, then we would have a straight line without a discontinuity. But because we're dividing two terms in such a way that we cannot allow x to equal 2, because that would cause division by 0, that means that we have a graph like this. So what they're going to have us do is fill in these values as we get closer from the left and from the right. So here we're aiming for 2, and they wanted us to do 1.75, 9. Yeah, and then they just keep increasing the number of nines, and you can do that forever. On this side of the fence, we've got 2.01, 2.01, 2.1, and 2.5. So from the left, you can see that the function is getting awfully close to 1. And then from the right, same thing. Like in others, if we're coming from the right, we go through these larger values down to the smaller values. So you can see they're converging to 1. And then on the graph, you can confirm that by seeing that no matter which direction we're coming from, um, we're going to end up with this result. Okay, so as we get closer to 2, the function is getting closer and closer to 1 without ever actually reaching it. So we call that the limit. All right. Now, oh, see now here they're essentially doing the same thing. They're saying, listen, let's plot this thing out. And we don't have to do every single one of these. Here it turns out to be 2. Um, the problem with this one is that, well, actually, let's look at the graph for a second. I want to see where this, here it is. Yeah, you can see that as x approaches 0, that would lead us to trouble because that would give us division by 0. Okay, so that's what this one is all about. So if you try the values of x coming from the left towards 0 and from the right, though, you can see that the actual limit is 2. There it is. It's 2. All right. Can you tell if you look at the chart from from the left and from the right, we're getting awfully close to 2. Now, this is a very time-consuming process, as you can see. Later on, we're going to learn, like I said, rules that will let us do this directly. Oh my God, it's raining like you couldn't believe. Excuse me 1 minute. I have some windows to close. Man, all of a sudden, completely out of nowhere, it's raining like it's like a monsoon out there. But all right, anyway. So yes, we're going to learn how to do this with a set of rules. Now, it turns out for some functions there is no limit. Okay. And so here would be a classic example of this. Why is there no limit in this case? Well, first of all, you can see that if you're trying to take the limit of this absolute value of x over x, if I try to substitute in zero here, you can see I'm going to get division by zero, which implies that there's a discontinuity here. But it's even worse than that. This discontinuity, there's only a single point of discontinuity. Sometimes it's called a removable discontinuity because I could actually define another value here and I'd have all the values that I need. This is different. The function behaves very differently coming from the left and coming from the right, and they never actually meet each other, as you can see. Um, so that means you can see the way they've defined this. This is defined as a piecewise function, meaning it's defined in multiple pieces. It's almost like two different pieces are being glued together to create a new function. This notation is what we'll be using to indicate something like this. Let me put it in here somewhere. And of course, that's because it's the absolute value. When x is positive, this is just one. But when we get to the axis, the vertical axis, we have division by zero. So on the right-hand side, as x approaches one from zero rather from the right, have this behavior. But down here, we're reaching towards -1. Okay. So there's a problem. Let's see. Actually, let me move this up here so you can see it differently. Actually, let me draw that again. Hold on. No, I didn't draw it correctly. Hold on. Now, of course, sometimes I've noticed with this tablet, the eraser gets funny. Let's try that one more time. Just to make sure everything's clear as it can be. So down here, we're approaching x from the left. Let's make that clear. And so the limit as x comes from the left is -1. It's coming from the left. It's getting closer and closer to -1 as long as we're coming from the left. On this side of the fence, as we come from the right, this +1. Now here's the problem. They're different. That's the problem right there. And that means the limit as x goes to 0 does not exist. Okay. In other words, there doesn't have to be a limit at every point on a function. And in a case like this, you can see visually just by looking at the fact that it's not just a discontinuity. The function is actually behaving very differently on either side of this point. And so that's how you can tell just by looking. There is no limit here. Okay. So that's the case you might run into. So here, they're trying to help us out here. There actually are three cases where you might run into a situation where there's no limit. Okay, so first of all, this is the case we just looked at. F of x approaches a different number from the right than from the left. C is just some constant or other. So that implies that there will be no limit. Oh, that, by the way, this graph is for this part that we're about to look at. The limit does not exist if 1, and C is just some constant or other. Okay. And we just saw this case. Or possibly number 2, f of x increases or decreases without bound. So let me show you an example of that. So the case I'm thinking of here is this one. This is what 1 over x looks like. And if you notice, the vertical axis is an asymptote. So as x approaches from the left, 0 that is, you notice how the function is getting very, very small. It's rapidly approaching negative infinity. Whereas on the right-hand side, it's the other way around. And again, because the two are not the same number, they're not both positive. If they're both positive infinity or both negative infinity, we'd be all okay. That actually would be the limit, but that's not the case here. So here we say that the limit does not exist. Okay. So you can see why that's a problem, because as we're coming from the left and the right, they're not the same. And one is going to negative infinity, one is going to positive infinity. Now, by the way, I'd like to show you another case, which you might think, well, it's the same one, isn't it? But it's not. Imagine we have this situation. That one actually looks a little bit different. Okay, well, that's not the best graph I've ever drawn in my life, but you get the idea. It's curved. You can see that unlike this one, both of these curves are approaching the axis, but they're never quite reaching it. But here it's happening instead of the first and the third quadrants, it's happening in the first and the second quadrants. In other words, as we come from this direction, the function is approaching infinity, and the same thing is true from the right. So that means in this case, there is a limit, and it's just infinity. The limit can be infinity. Okay. It can also be negative infinity. But of course, it requires that the limits agree with each other from both directions. And that's what we're seeing here. So that's why this case is very different than this case, where they don't. Okay. Actually, let me make this a little neater over here. And this one would be y equals 1 over x squared. Okay. And then now here's this is a very bizarre case. It says that it oscillates between two fixed values as x approaches c. Now that's very difficult to visualize. That's why I went ahead and did this ahead of time. This graph is the graph of over x. And you can see it goes up, down, up, down, up, and down. As we approach zero, it keeps alternating back and forth between two different values. And it never actually converges to a single number. So here, it's you can say either it's undefined or it does not exist. Actually, I think when you're doing the mind taps, it likes you to say does not exist, but they'll tell you what they want you to do. But for any other case, the limit exists. It's just a question of finding it. Okay, so once you know when the limit doesn't exist, that helps a lot because that way you can rule it out. When you run into these cases, um, you'll start to understand when you can and cannot calculate a limit. So but the rest of the time, and these are very unusual cases, by the way, most of the time there is a limit. The question is, how do you find it? Okay, so now the formal definition of limit is extremely theoretical. You can see that it's all in Greek letters, and but what they're essentially trying to say here is this. Let me make this a little bigger. They're basically saying that in English, I'm trying to find where they're trying to explain it. If if we're within, see what they're trying to do. If you look at this graph real fast, here it means f of x is in this interval. So, I mean, you may remember seeing this symbol in math. This means is an element of the set. In other words, it's a member of a specific set. So here's L, here's C. Here's C is the constant. L is the corresponding limit. And so what they're trying to get at is the idea that this limit exists as x approaches C because um, there is a small number delta. The deltas are down here, by the way, such that if f of x is in this interval, then we can find a delta. And by the way, I was supposed to introduce these letters to you just in case you've not run into them before. I almost forgot about that little detail. Um, this, you've seen this letter before. This is the uppercase delta in the Greek alphabet. You know how it's used for change, okay? But this is the lowercase. You don't see that as often. And then this is epsilon. All right, so there's our Greek lesson for the day. All right, so anyway, so what they're suggesting here is that if our function is within that interval, in this case, between these red lines, then there's got to be some delta out there such that x is in the interval. between C minus delta and C plus. So what are they're basically telling us is that as we get closer and closer, as x gets closer to c, f of x is getting closer to L. I mean, that's really all it means. It's just a very abstract way of saying this. It's claiming that being within this interval here implies that this also holds. Now, they might, I'm not sure if MindTap is going to ask you to do this. Um, yeah, this is the example that they're giving us. I guess we'll run through it once, and then if you need this for MindTap, maybe we'll go over it again. Um, let's say the function is you're told, or you want to know if this is true, okay? Or how can you prove that this is true? All right, fine. So, 2x minus 5 is a straight line, no discontinuities. Whoops. Nope, that's not a good graph. As we approach 3, the limit is 1. Now, this is one of those cases where there are no discontinuities or anything like that. So that means in a case like this, to find the limit, you're literally just substituting the value that you're approaching into the function and you come up with your answer. Most of the time, that's all you have to do. You just literally substitute the number of the value of x into the function and see where it ends up. So what they're saying is, well, we know this limit is 1. But according to this definition, how can we prove it? Well, let's just say they want us to show that they picked an epsilon point of 1. It could be any small number. So remember, this is based, let me go get a copy of this graph so we don't have to keep going back and forth. Well, actually, I think they have a copy right here. Let's go grab that. Here we go. So yeah, I mean, this is the limit. As x goes to 3, the limit is 1. So, and it's the epsilon goodness is 1. So since the limit is 1, L minus epsilon is 0.99. L plus epsilon is 1. Whereas down here, remember, it was written as x, and the following definition. Oh, right. X minus c has to be less than delta. Or you can think of this as And since L is, we've already shown that L is one. So what's basically what they're saying is we should be able to identify some delta, for which this is always true. And the way they're going to have us do this is compare one on the left is x minus 5 minus 1 is f of x minus L. The one on the right is x minus the limit. No, wait, sorry. Um, X minus f of x. Let me make sure I write this out correctly. Oops, hold on a second. I'm sorry, I wrote it wrong. It's x minus c. C is this point right here. Okay, now we're getting somewhere. All right, now what are we supposed to do with this information? The one on the left is supposed to be less than epsilon. We already were told that epsilon is 0.01. Or so then we have to demonstrate that this implies that x minus 3 is less than whatever delta is. We have to show that there's some delta out there where this relationship holds. Okay, so the reason why I set it up this way purpose is so that to simplify it, because 2x minus 6, it would like you to notice here that this is the same thing as 2 times x minus 3. So if you divide out both sides, you'll see that x less than 3 less than 0.1. Okay, and so okay, uh, oh, sorry, wait a minute. I did something wrong. Hold on a second. This should have been divided by 2. All right, now we're good. So you can set this equal to delta, and you're good. So in other words, we found a constant delta such that we're guaranteed that this function is within epsilon of the limit. Okay, and in fact, you could pick any ones you want. Any epsilon you choose, there's going to be a corresponding delta with the same property. So this is the formal proof. Now, I did mention before that sometimes these theories that are underlying what we're learning are very complicated, very abstract. After this, you will just be using rules. I don't know if MindTap's going to actually ask you to do one of these, but going forward, we're going to see a lot of nice, straightforward algebraic rules that let us calculate limits. So, yeah. Now, here's one where they would like us to plug in some numbers and use that to come up. You can see what's happening here is they're getting awfully close to 3. I guess we could throw these into Excel real fast. So the values they want us to use are that's 2.9, 2.99. On the other side, we have, oh, I looks like I drew this incorrectly. This belongs here. There we go. That's better. All right, 2.999, 3.001, 3.01, 3.1. So I'll just calculate this function each of these x's. And we'll see visually what this is supposed to be. So it looks like it's getting very close to negative 0.1. Okay. Now you notice that with this one, we can't really simplify it. Actually, maybe we could, but even if we could, you could see that coming from the left and from the right, we're getting awfully close to negative 0.1. And there's the answer. Okay. Now this one, they're not even going to ask us to solve for a table, because if you notice with this one, you can just solve for it directly. Meaning if I plug it in, the value of x, I'll get my answer directly. That's kind of nice. It's a nice change of pace when it's that easy. And there you go. Now, if you want, we can draw a graph of it and see why this is happening. X squared plus 4x in Symbolab looks like this. And they're asking us to figure out what the value of the function is as x approaches -2. So looking, it's hard to be sure. Oh, there it is. This is it. This is what they're looking for. -2 corresponds to a y value of -4. So that's the answer. All right. So in other words, you notice how this is a nice continuous function. So to find the limit at any given point, literally all you have to do is solve for the function at that point, and you have your limit. And you can see that the limit will be the same coming from the left, coming from the right. So when the functions are well behaved like this, calculating limits is actually very straightforward. It doesn't seem like it at this point, but that's yeah, where we're heading. All right. Now that was section 1.2. So 1.3 is where they're actually going to start showing us some of these rules that I've been alluding to. Um, so so they're mentioning here, for example, the case of direct substitution. And so that means that the limit as x approaches c of f of x is simply f of c. And let's just make a couple of quick examples. The one we just did, this is an example of that direct substitution. So in other words, the rule, the formal definition is this. So as long as you have a function that doesn't have any discontinuities, you're in pretty good shape. So in other words, imagine you had, let's make up a quick simple one. What will be the limit as x approaches 2? Okay, there you go. And again, if you for some reason decided to solve for the limit coming from the left or from the right, you get the same answer. If you filled in one of those little charts, for example, with the values less than 2, you'd see they're getting closer and closer to 8. If you then did the same thing, coming from the right with the larger values, the same result. And ultimately, your answer will be 8 rather. All right. So that's a fun case. It's easy. All right. If only they were all that easy. The limit of a constant is just a constant. Here you've got the limit of x is x approaches -4, so that's just -4. And then here with the 2, you just end up with 4. Now, once you have that straight, now these are just some extensions of this, and you can, yeah, I'm sure you can see these all make perfect sense. The constant you can factor it out, like you can factor out a constant if you need to, but you don't have to. Direct substitution would have left us with this. It's the same thing. Then they're also showing us that the sum of a limit is the limit of the sums. Same thing with the differences. The product of a limit, the limit of a product is equal to the product of the limit. And of course, the ratio of the limit of a ratio of functions is equal to the ratio of the two limits as long as the denominator is not 0. All right, so these are all pretty straightforward. Let's quickly do, and by the way, you can break this up into individual pieces. You can simplify quite a bit with these rules. For example, x approaches 2, or x squared plus 3. So here's what you can actually do. Now remember, here you're just substituting. And the limit of 3 is just 3. 19. And it's that straightforward. After that epsilon and delta business, you're probably terrified, but now you can see this is not that difficult. At least these are not. And here's the graph. You can see that you just find where 2 is, and you can see the corresponding value of y is 19. Now again, for a ratio like this, as long as you don't have division by 0, you're all set. Like here, now if you notice here, -1 is not in the domain, but it doesn't matter because the limit is as what, sorry, x approaches 1 and not -1. So in other words, if you run into a case like this, if we're looking for the limit as x goes to -1, then we have to be very careful. But because 1 is not the point where the function has division by 0, we can still just go ahead and plug everything directly in, and we'll get our answer. And you can see that that's exactly what happened here. Uh, let's see. So yes, there is potential for division by 0, but luckily we're not being asked to find the limit as x goes to -1. So yeah, first 1 squared plus 1 plus 2 all over 1 plus 1. And it's just ooh, radicals. Wow. This is getting very intense. All right. So, you know what? I'll tell you what, since it looks like we're done here, the next session we'll just carry on with all these rules, and we'll get a lot of practice solving for limits when we don't have to worry about discontinuities or anything along those lines, or division by 0. So we're going to learn the basic rules. Now, as it turns out, even then, we're going to run into some situations where we have to learn something more involved. Um, but we'll get to those later on. In other words, even here with the rules, the algebraic rules, we can run into some very complicated cases. So we're going to see how to handle those as well. But first, let's focus our attention on here, solving with direct substitution, and then we'll address the more complicated cases later on. All right, so wow, that was a pretty tough session, but you know, it's not always that theoretical, okay? We always have that as our basis for what comes next, but um, what we're really trying to do is understand how to use the rules so we can solve problems. All right. Anyway, now, I mean, if you want to become a theoretical mathematician, then you're going to focus your attention on the theory. But if you're going to use it for something practical, then you're going to be focused more on the rules. So anyway, so I'll have to stop it here, and I'll see you all next time.